Our lessons on determinants and Kramer's rule. The way that you should handle doing this is not necessarily writing down each thing. You should have your book out and you should be working on the problems as you go, and then following the directions and instructions and pausing as you go through this rather than listening to it all in one big giant lump, so that you're listening, you're seeing an example while you're doing that. So first we need to talk about the fact that all square matrices have something called a determinant. And that determinant does boil down, after you do some calculations, into one single number, one real number, which, as you know, means a decimal or a fraction or a whole number or an integer, but it does break down into being one real number. The symbolism for a determinant looks very much like absolute value bars, but it's really its own type of matrix. So these sides tell you that this is a determinant, and then there are elements in it just like there are in a matrix. So you can find the determinant of a matrix by doing certain operations. A 2 by 2 determinant is very, very easy to calculate. You'll have a number in each one of these places, and you're making like a crisscross shape. You're going to multiply these together and then subtract and come back and multiply these together. Our formula looks like this: A times D minus B times C. And if you do even, mentally make this swirl as you're going through, it's very, very easy to calculate the determinant of a square matrix. For example, for this square matrix, we would take 2 times 1 minus negative 8 times 3. 2 times 1 minus negative 8 times 3, which becomes 2 plus 24. And so the determinant of this square matrix is the number 26. We do use these determinants for something called Cramer's rule, so they're not just existing for no reason. The way that this would be good, even though the process is difficult, the calculations, as you can see, are very, very simple. And so even if it looks like, wow, that's an awful lot of things to write down, it is a good method to use if for whatever reason you don't have a calculator, provided you can remember the steps. The determinant of a 3 by 3 matrix is a little bit more difficult to find. There are two methods to finding the determinant of a 3 by 3 matrix, but what we're going to do is take a look at the process that's called finding the determinant by minors. And when you find the determinant by minors, you really are going to break it down into 3 separate, smaller 2 by 2 matrices that are easy to solve, like we saw a second ago, and using these numbers that are in your 3 by 3 matrix. Let's take a look. So what you're doing is you're taking this one, the upper left, and then these 4 numbers here. So you'll take this number times the determinant of these 4 minus this number times the determinant of these 4 numbers plus this number down here in the lower left corner times the determinant of these. It's not quite as bad as it sounds. Like I said, it's more of things to write down and keep track of, but the actual calculations are very, very simple. So for example, if I have this matrix and I want to find its determinant by minors, I'm taking the determinant of 1, I'm taking the number 1 times the determinant of these 4 numbers, minus negative 1 times the determinant of these 4 numbers, plus 1 times the determinant of these 4 numbers. It looks like this. 1 times the determinant of these four numbers. -1 times the determinant of these, and 1 times the determinant of these numbers. Then what you need to do is you need to keep this 1 and you're going this way minus this way. Minus negative turns into a +1 times 6 minus -2. +1 times -9 minus 4 by taking down around through. And then keeping track of these processes, and then finally doing the last little bit of calculations. Each one of these calculations, especially with pencil and paper, is fairly easy. It's just a matter of getting the hang of the process. And that brings us to this idea of Cramer's rule. Cramer's rule is an alternate way of solving systems. It's not necessarily the most elegant. Substitution, elimination, solving by graphing, using a table, all those different ways are good ways. This is just another way that can be used to solve, to find x and y when you've got equations in standard form. So Cramer's rule says that if you make matrices out of the coefficients of x and y, that'll become the denominator of your answer to solve for x. And if you make a matrix to find the determinant out of the leftover numbers, so that these are the coefficients of y, and since you're solving for x, you take these c's and you put them into that column. By following this rule and then doing that, finding the determinant, you can very quickly solve for x. It's kind of like, it's just kind of like a quick way if you can remember all the steps. Y is very similar, but what you notice is still the same denominator made up of the coefficients of x and y. The x coefficients stay right here, but since we're solving for y, they get replaced with these numbers out here. Now, as far as the derivation, where it came from, we'll just kind of leave that one alone, and we're just going to practice using this. So here's a sample. So A is 3, B is -2, C is 10, A is 4, B is 5, C is -3. So what we can do then is we can take these numbers and begin to plug them in to these formulas. So our starting denominators will be 3, -2, 4, 5. 3, -2, 4, 5. Our numerator here, to solve for x, would have our 10, -3 in here. And you'd have your -2, 5 in here. Here we would have 3 and 4. And here we would have 10, -3. Solving for x and solving for y, just as I just pointed out. Then we know that the determinants for a 2 by 2 are very simple to solve. 10 times 5 minus 6, 50 minus 6, 15 minus -8. Here we'd have -9 minus 40, 15 minus -8. And you get these answers, 40, 23, -49, 23. It's a very nice way of solving, especially these answers are kind of like weirdo fractions. If you tried to solve this by substitution or elimination, you might have a bit of difficult work. The work here is very simple. It's just multiplying and subtracting, multiplying and subtracting. It's just a matter of which numbers to multiply and subtract, and we've got our solution just laid out here very nicely for us. So in the case of equations in standard form that have two variables and you want to solve that system, Cramer's rule actually isn't too bad. It's nice simple process, just remembering what number goes where. So once again, to reiterate, these four numbers are the denominator numbers, and then the C row replaces whatever number you're trying to solve for. When we move to equations in three variables, a system of three equations, three variables. Remember, it does have to be square matrices, so if you've got three variables, you have to have three equations. When we do this, it looks like a long process, and I'm running through the steps and showing them to you. As I said, I would recommend that on the homework, you sit with the homework and watch the processes and run your own examples using these processes as you go through, and pause this video so that you're able to find your answer. So our denominators are all going to be the same. The interesting good thing about this too is that once you've figured out one of the denominators, just use it the next time. You don't have to put all the numbers in again, because these denominators are all the same. A, B, C, 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 A, B, C. So it's all the coefficients of X and Y and Z in that order. Those are our denominators. The numerators replace the row or the column that you're trying to solve for with the D values. So for example, if I'm trying to solve for X, this would be D1, D2, D3, and then these would be the same. Here we would be replacing the middle column with D1, D2, D3, and here we're replacing the last column with D1, D2, D3. So it looks like this. When you break it down that way, it's not too difficult to remember. The difficulty comes in there's just a lot of multiplying and subtracting in these things, especially in the 3x3 matrix. You may have a different favorite way, but let's just make sure that we get this taken care of. So we have here a system of three equations and three variables. And so we want to plug in all of these numbers, all the ones and negative ones and the other numbers. The trickiest thing is being very careful to put the right number in the right spot. So down here in the denominator, we'd have 1, 2, 1, 1, negative 1, negative 2, negative 1, 1, 3. And I would suggest that you do it that way and fill in that denominator first, and then it's just a matter of pulling the numbers up for the two rows and replacing the one row with these numbers. So here we have the numbers replaced just as I just described. 2, negative 5, 4, this is the one you're solving for. Here's all of our coefficients, 1, 1, negative 1, 2, negative 1, 1, 1, negative 2, 3 that come from here. But then the numerator and the denominator both have to be then calculated using minors. Remember, we have used the number, Kramer's rule, use the number times this, minus the number times these, plus the number times these. The denominator has the same thing happening. 1 times this determinant minus 2 times this determinant plus 1 times this determinant. And then mathematically, this part's easy because it's just negative 2 times negative 3 minus negative 2 plus 5 times 3 minus 2 plus 4 times 1 minus 1. And then similarly for the denominator. This denominator is 1 times -3 minus -2, which gives you -1. -2, 3 minus 2, which is 1. 1, 1 minus 1, which is 0. Simplify these things out, we get -7/3, and that's our x value. So a lot of writing, but the math being super easy. This one actually is a little bit nicer than having to solve by elimination in some cases, especially with this fraction, these fractions that come up. It's very easy to get lost. Any of them, it's easy to get lost in the process. But since these are all integers that you're dealing with, it does make it just very much nicer, and you only end up with a fraction at the end. That one's there, brought down small. We're going to tackle y now. Notice we already found that -3 was in the denominator. We can keep that. We don't have to recalculate it. This is the one that's replaced because we're solving for y. Once again, 1 times this determinant minus 2 times this determinant plus 1 times this determinant. And then once again, 1 times -2 minus 4. -2 times -6 minus -4 plus 1 times -2 minus 5. And -2 minus 5 is -7. -6 minus -4 is -2. -15 minus 4, -19. Simplifying negative over negative, we end up with 22/3. Y is done. And then tackling z in the same way. Same process, -3, same denominator, no problem. But you're replacing that z column. Same process, 1 times the determinant of this minus 2 times the determinant of these plus 1 times the determinant up here. Same process, crisscross, crisscross, crisscross. And this one comes out to be a nice even 7. So by the time we're done, we have this very complicated solution to this system, but it really wasn't a whole lot of difficult math. It's just remembering what to do. And if you followed along and you did another example from your book or your homework question while you did this, then hopefully it made even that much more sense. I would suggest anywhere you get stuck that you go back and just rewatch so you can see. Kramer's rule applies sometimes, but there are some times when it doesn't work. We know we can't have a 0 in the denominator. So even before you go through all of that, you might want to check out the denominators first, because if the denominator turns out to be 0, then Kramer's rule doesn't apply and you'd have to find a different way. So there's no point in doing all of that work without first checking the denominator. So for example, if I have these, there's another equation that's missing here. There should be another one. So that I had 2, -3, 4. 2x minus 3y plus 4z and equals something. So if we had this and we went to figure out our denominator and we went through the process, and when we find out that going through the process gives us a 0 in the denominator, we'd say Kramer's rule does not apply. It doesn't mean that there's no solution necessarily, but it does mean that Kramer's rule isn't going to help us out in that situation. So there you have it. Determinants, you've learned what a determinant is and how to calculate it. And you've also learned about Kramer's rule and how to tell when Kramer's rule just doesn't apply to a certain situation. Watch this as many times as you need to so that you can become confident.